Okay, so today I want to talk about some really powerful ideas from projective geometry, which have to do with things called harmonic ranges and harmonic pencils. So basically, what we're going to see is that there are certain symmetries and aspects which appear in different projective forms, which are just about indestructible and essentially inject some very important numerical relationships into lots and lots of forms. And these particular harmonic relationships are completely invariant under projection. And they're remarkably powerful, and it's surprising how many different places you can find these harmonic ranges. So I'm going to start by defining what these things are. It's a fairly simple numeric definition. And then we're going to look at some examples of where they can appear. And we'll see that they're very closely related to these quadrangles and quadrilaterals. Those are shapes formed by 4 points and shapes formed by 4 lines. And then we're going to have a look at some other really interesting kinds of relationships between those two. And finally, we're going to look at a really fascinating construction called the 13 configuration, which is basically a lovely setup where you have a quadrangle and a quadrilateral and a few other things, and you end up with 13 points and 13 lines, and you can see all these duality ideas all working together in tandem. It's a very, very lovely construction. Okay, so now I'll describe this idea of a harmonic range of points. Suppose that on some line we have 4 points, A, B, C and D, in different positions along this line in our projective plane. And just for the time being, to make things simpler, let's imagine that we can actually measure displacement along this line. So in particular, we'll just do the normal Euclidean style thing. We will suppose that there are some measurement marks on this line. We could create these in projective geometry by getting a sort of unit measuring stick and then projecting it and shifting it along the structure. But anyway, we can imagine these marks, and so we can have this idea of how much displacement there is between one point and another. So I use this notation A, B over bar to represent the amount of displacement you have to do to get from point A to point B. So it's convenient just to think of A and B as points on the x-axis, or simply as numbers. And in that case, we can think of AB over bar as B minus A, because it represents the amount of displacement you have to do to get to B when you're starting from A. So A plus B minus A equals B, right? So we can see the actual mechanics of this going on in this diagram. I've put these 4 points A, B, C and D down, and it doesn't matter how you place them. You can put them in different orders and all sorts of things. And in that case, the definition of whether a harmonic range is that we'll say that A, B, C and D are a harmonic range when they satisfy this relationship here. What this essentially means is that if you look at point A and you look at how much displacement you have to do to get to B and divide that by the amount of displacement you have to do to get to D, well, that gives you that proportion in this case here, that's going to be equal to minus 9 over minus 18, that's a half, isn't it? So that's how A divides the segment externally. Now we look at the other part of this, which is C, and we'll have a look at how C divides this segment internally. So to do that, we're going to be looking at the quantity CB, the displacement you need to do to get from C to B, which is 3. Divide that by CD, which is minus 6. So you get minus a half. Okay then, so we do indeed have the way this segment... Okay, so we do indeed have the way A divides BD externally is similar to the way that C divides the interval BD internally. And therefore we have that AC and BD are harmonic conjugates to each other. This is a kind of symmetric relationship that they have. So this idea of harmonic ranges is really a very interesting one because it appears in so many places, and more importantly it's what's known as a projective invariant. That means that if you have a harmonic range and you do a projection of it as perspective or something, then the result will be another harmonic range. So for example, we can just add this purple point down, this sort of viewing point, and we can do a perspective from our original harmonic range, A, B, C, D, and then just seeing where these pencils coming out of our viewing point, seeing where these lines coming out of our viewing point meet these other points here. You should note that these black points on this green line also form a harmonic range, and this is always going to happen whenever you do a perspectivity of a harmonic range. You get a harmonic range. In fact, whenever you do any projection at all of a harmonic range, you always get a harmonic range. Now this is an incredibly important point because of how many different kinds of harmonic ranges occur naturally. The fact that they can't be destroyed by projections, which can really warp the way things look a lot, is quite remarkable. And also, it allows us to think about another thing, which is the idea of what's called harmonic pencils. So you see in this lower part of the diagram, we have this purple point here. Now the pencil of that point is the set of all lines that pass through the point. But this is a so-called harmonic pencil. We've just got 4 lines. But the way those 4 lines pass through this point has this kind of harmony to it. Because, well, essentially, if we just draw a line which meets each of these 4 lines exuding from the purple points, well, that line is going to have a harmonic range on it. So the harmony is really coming from the angles at which these lines are making with each other as they meet this purple point. So it's called a harmonic pencil because it's all about the way that the lines are chosen to come out from this point. So this set of 4 lines is a harmonic pencil with respect to this point here, and this set of 4 points is a harmonic range with respect to this line, the x-axis. Here's an example where harmonic ranges occur. I found this in Norman Wildberger's course on universal hyperbolic geometry, and essentially the idea is this. Take a point A outside of a circle. Now, to find the kind of dual of A, which is like a line, what you do is you find the lines out of A which just touch the circle tangentially. You're kind of making the smallest V shape possible, which holds that circle inside it. And then those lines are going to touch the circle in 2 points, link those 2 points with a red line, and that red line is then the dual of the point. So I've spoken a lot in my discussion of projective geometry about how there's this duality between points and lines. Well, this Apollonian construction here really allows you to find the dual of a point. After you've made this thing, if then you draw any line you like from A, which passes through this circle, well, let's call the point where it enters the circle B, and the point where it crosses this polar line C, and the point where it leaves the circle D. Now it turns out that A, B, C, D is going to be a harmonic range. And that's for any line going through this thing. So already you can see that there's an enormous number of these different harmonic ranges occurring. And perhaps you would like to try this. I mean, it's quite instructive to draw out something like this, and you can just use your tape measure and check that indeed AC is harmonic conjugate to BD. So I just showed you how you can get lots of harmonic ranges by looking at those kind of Apollonian constructions involving circles. Here's a way you can get some harmonic pencils. So remember, a harmonic pencil is just where you have 4 lines coming out of a point that have this kind of harmonic relationship. So to do that, one way is to just get any point with 2 lines meeting it, and then just look at the angle bisectors. So if we add these angle bisectors in, these blue lines here, which are cutting the angles in half, well, those 2 angle bisectors are going to be perpendicular to each other. But what's more is that actually these 2 red lines and 2 blue lines now form a harmonic pencil. So just to check that, we could draw a line and then just look at this line and look at where these 4 points intersect this line. And if you have a look at those 4 points, you will see that they are in fact forming a harmonic range. One rather lovely way of getting harmonic conjugates is simply to take a quadrangle, in other words any 4 points in the plane which are not all along the same line. And then if you do that and draw some lines between these points, filling out the quadrangle, you notice various special points appear. So I've just reorganized things a little bit. And then you should notice that once you've got your quadrangle filled out, something like this, you can then add an extra line. I add this orange line here, which has the issue that it meets 2 of these new points which get formed by adding new lines to the quadrangle. And if you extend off this line, you find that it also touches this almost horizontal black line in the middle here. Actually, I shift things around a bit so we can see exactly where it does meet this extra point. So this is a special line of our quadrangle. And so essentially our quadrangle is making these 4 special points on the line. Now the interesting thing is that this is actually a harmonic range. So let's have a look at it. And you can see this because A divides CD externally in the same way that B divides CT internally. In other words, if we take the ratio of AC the displacement for A to C divided by the displacement from A to D, well, that gives us this number here, which is roughly 0.3, I think, 0.3. Well, if we do the same thing from B's point of view, we get a number which is equal to about minus 0.3. That is, the displacement from B to C divided by the displacement from B to D is about minus 0.3. And so then, if we just take the ratio of those two, we find the answer is actually minus 1. Okay, so now I'm going to do a construction which is pretty much the dual of the previous one. Rather than starting with a quadrangle, we're going to start with a quadrilateral. So that's 4 lines. And you can see that these 4 lines are defining some points where they're meeting. And so in fact 6 points get defined this way. And so we're going to use this quadrilateral to make something which has more of these nice harmonic properties. In particular, we're going to make a harmonic pencil. And we're going to see how that comes about quite naturally, just by looking at these different points which get defined by this quadrilateral. So 2 of our lines are defined like this, and they meet at this point. So that gives us another point to examine. And then if we join this new point we've created to the place where, well, to another one of the meeting points of our original quadrilateral lines, we get this pink line here. And then we can draw this green line, which functionally is kind of similar to the pink line. It connects the joining spots of the orange lines with an extra point of the quadrilateral. And so now the claim is that these 4 lines, orange 1, green, orange 2, pink, are a harmonic pencil. So what is a harmonic pencil? Well, a load of lines going through a point are a harmonic pencil when any line that they all go through, the intersection points of that line with these exuding rays, makes a harmonic range. So if this truly is a harmonic pencil, then if we just add an extra line onto this picture, like say this black one here, and look at all the places where these 4 lines meet this new line here, well, that should give us a harmonic range. And if we do the measurements, we find that indeed we do have a harmonic range. And so in this case here, if we label the points like so we're labeling them A, B, C, D, going from right to left, and we're thinking of positive being going left, in that case it turns out that the displacement from A to B divided by the displacement from A to D is equal to -1 times the displacement from C to B divided by the displacement from C to D. And so A divides BD externally as C divides BD internally. And so they're harmonic conjugates. And this is a harmonic range, and so we have a harmonic pencil. Okay, so they say a picture is worth 1,000 words. Well, I think this particular picture might be worth even more, because it really expresses a lot about the things we've been talking about to do with quadrilaterals and quadrangles and harmonics, all in one picture. So this is called the 13 configuration, and essentially it involves 13 lines and 13 points. And if you look carefully, you can see I've coloured these points according to different functions. So how's best to show this? Perhaps initially, if I hide the blue lines, and well, yes, I think that's good enough. Okay, so if you just concentrate on the 4 dark blue spots, that's 4 points, non-collinear, in a plane, that forms a quadrangle. Now, we can make that into a so-called complete quadrangle by adding all possible lines between those points. And when we do that, we generate some extra points. For example, these light blue vertices could be considered the extra ones generated. And we also get this central thing. And now, as I've shown you with a previous construction, when we make one of these complete quadrangles, we end up having these 4 points meeting on a line. So in particular, just adding all the possible black lines automatically generates these 2 external points here with the light blue shade. And then we also get a point inside, and joining that point inside to one of the other corners gives us, well, our other 2 different, say, legs of this quadrilateral. So we have these 4 lines sticking out, which have points on them in a line. Now these yellow points here, these are basically forming the opposite triangle of this quadrangle. And if we carry on going then by drawing out, so already we have some harmonic relationships. I mean, in particular, these 4 points here in this green line are going to form a harmonic range. But what's interesting is that we can also think about a quadrilateral. So we can draw these blue lines in just to meet the places where the red line escapes the original shape. And they naturally correspond to adding an extra 4 lines to our picture. And so now we do indeed have the 13 configuration because we've just added an extra 4 lines. It's interesting about this number 13 as well. Well, let me just say before that, what about these 4 lines? Well, they form a quadrilateral, a 4-line shape, and that is related to the triangle as a kind of go-between to get to the quadrilateral. So basically we can see the duality at work in this picture. There's really a lot to take in here. I urge you to sort of pause the video and see how many different harmonic things you can see. Because, for example, now we can see that we have we have harmonic pencils in different places from this quadrilateral, as we showed independently before. You can also note that the lines are split up into groups. So we have 6 black lines and we have 4 light blue lines, so that gets us to 10, and then we have 2 red lines, that gets us to 12, and then 1 green line, that gets us to 13. So the lines are arranged into groups according to different functions, and that ends up making 13 objects. And also with the points, we have that there is a group of 6 points, which are the vertices of the quadrilateral, all the complete set of vertices formed by that quadrilateral. And we also have a set of 4 points, and we also have this diagonal of 3 points, this diagonal triangle of 3 points. So that gives us 13 points.